It is not my head. But I'm glad he's been able now because it's also very good at explaining things. People doesn't seem to mind no matter how many times needed. The areas we worked on, I think from what I was following was first was seek and find criticality, where at a critical point that in the case of freedom, you don't have either side. They have liberated only at the critical point. That's very interesting. We worked on that. Then we worked on things called Fermi arcs. Fermi arcs are where Fermi circuit is not really a closed circle or closed anything, it's open. And you can wonder how that makes sense, and that's what happens in these topological insulators. Then he worked on this bilayer graphene and multi-layer graphene. So that's what you can talk about today. These are graphene seeds, which you put them on top of each other and you rotate them at a magic angle, all kinds of things appear. Superconductors, current bands, quantum Hall effect, all this, things that you heard about but never saw. These got 2 layers, 3 layers, and similar things. So I'm going to invite him now to take over at the end to have questions. And answers.
Thanks, Shankar. It's very hard to follow an introduction like that with an actual talk. So maybe next time, let me present the talk and then you do the introduction. Yeah. So I'll tell you about some very exciting recent developments, both experimental and theoretical, I'd say, in condensed matter physics, which has to do with these moiré lattices. I'm sure all of you have heard about it at some point or the other, but I'll try to review it a little bit, both the experiments and what we think is interesting about the theory. I imagine this would be a very informal kind of presentation. I didn't realize there'd be this kind of gladiator style arena. But feel free to ask questions and interrupt. I don't have to get through everything. I'd really appreciate it from my point of view as well to make sure things are getting across. Okay, so basically what we are going to be interested in is a system that looks like this. I didn't have to get through all my slides, but I was hoping to get through at least one. There you go. Oh, I see. Okay, good. So you start with a sheet of graphene, a 2-dimensional carbon sheet. The recent advance has really been with people taking another sheet, rotating it, and putting it on top of the first one. Again, as you can see, it looks much better on the screen than on the computer screen rather than on the projected thing. You can see an array of something, right? A lattice is formed at a scale that's very different from the atomic scale. And really, we're going to be interested in the properties of electrons as they move through this periodic moiré pattern. And this is really a new approach to creating a crystal lattice, something that can influence the motion of electrons. And there are many things that are different that you can do over here. For example, just to show you one example, let's say I were to drag the graphene sheet on top across the screen. This is the lattice constant. Let me now drag the sheet. So that is what happens when you drag it sideways. You see that this moiré pattern moves. You can do all kinds of interesting things with it. And this will really open up, the hope is that this will really open up a new way to control electrons. Okay, so since this audience, I think, is broad, let me very quickly review some basic concepts about electrons and solids. So the fundamental distinctions that you have, metals and insulators, often can be explained in terms of how the electron motion is modified by a crystalline lattice. You get these bands. If you completely fill these bands, you get insulators. At partial filling, you get metals. And if you like, these insulators over here, in a way, they are like a vacuum for electrons. Okay, just like we have electrons in our vacuum, they are gapped. You've got to provide some rest mass to excite electron-positron pair. Here you have electrons completely filling the band. If you want to create one, you'll have to extract one from here. If you want to liberate these, extract one and put it in the higher energy band, conduction band, leaving behind a hole. This is sort of an artificial vacuum. Of course, all the energy scales have been changed. We go from the rest mass of the electron to this band gap, that's the equivalent. And in this way, you can modify different properties of the electron. Of course, people have been exploiting this for decades now. This is really what goes into the solid state transistors, for example. Back in the day, people could do everything you do now with transistors with vacuum tubes. So they literally use the vacuum, control the motion of electrons in the vacuum. And what the big revolution that came with the semiconductor-based transistors was that you could replace our vacuum with a much more controllable one, which is the electrons inside a semiconductor like silicon. And you could modify, for example, the effective mass, the energy gap for particles and holes, and so on. Okay, and so this is really what has helped us a lot in this, has helped the progress of electronics. Actually, it's interesting to go back to when people first demonstrated the transistor. One of the big, the notable differences that everyone was obvious to everyone. You don't have to wait till these things heated up, right? You turn the switch and they're on. That's a different aspect, I guess, from what we're talking about. But obviously, we're very grateful for all of these advantages that came with this. Okay, so now what do you want to do? That's been going on for decades. Can you actually get qualitatively new effects in a band? And I'd like to think about the recent sort of progress in the, for example, the moiré field and so on, as getting, really being able to modify qualitative properties of electrons. So if you want to capture the physics of electrons in a band, this is kind of the semi-classical theory. The position, the velocity, and the acceleration of the electrons can be interpreted in terms of these dispersion relations of potential. You also have the Lorentz force on the electrons. And the interesting thing about electrons in a band, which is qualitatively different from electrons in the vacuum, if you look at these equations, they don't quite look symmetric. Okay? There's no analogous term over here for the velocity. But in fact, electrons in a band, they have something known as an anomalous velocity that appears from the Berry flux, from the way in which the electronic wave functions change inside the band, and ends up giving you this new effect, additional term, an anomalous velocity, which ultimately gives you interesting physics. We'll see some of them today. And again, modifies the property of the motion of electrons inside a band. Okay, so this is part of the quantum geometry of the band, this the so-called Berry curvature, the thing that ends up acting like a magnetic field, but in the wrong part of the equation. And there are other quantities like this that appear once you have more interesting kinds of bands, different from the simple semiconductors I initially talked about. Okay, so here is an example of a system where you really get graphene electrons moving through this lattice of carbons. I won't go through the details, but eventually you end up getting a dispersion relation that looks like this. Neither a metal nor an insulator. The energy bands touch, so there's no separation between them. There's no identifiable gap. But at the same point, if you look at how these electrons disperse, they're not the usual quadratic dispersion that we are familiar with. That's the kind of dispersion we put into our Schrödinger equation. Instead, it's this linear dispersion. And if you're just interested in low energies, so your electrons naturally fill up to this point. Interested in low energy excitations, they're given by this equation, familiar from as part of the Dirac equation. There's no mass term. It really looks like the massless Dirac equation. Okay, so electrons and graphene, their wave functions are not a single component. Actually have two components. You've got to specify the amplitudes to be on the red and the blue sides. So they have a two-component structure. That's where the spinor structure that you associate with the drug equation appears in this context, and they have this kind of linear. And what we'll be interested in is how this moiré, this kind of periodic pattern, how that goes in and modifies particles that look like Dirac particles in 2 dimensions. And we'll see somehow these Dirac particles are very intrinsically topological in a sense. So we'll see that when you do this, you get very interesting bands whose characters are qualitatively different from what we've seen for semiconductors. Okay, another way, attractive way to think about this is that once your electron enters a crystal, it actually acquires a shape. It goes from being a point particle to something that now has more degrees of freedom. How much of the electron is sitting on the red versus the blue? This 2-component object you can think of, as we usually do in quantum mechanics, as a point on a sphere, on a block sphere. Okay, and as the electron moves inside the crystal, the point on the sphere is moving around. So it's got more degrees of freedom than what you would normally associate with a point particle, and that ends up giving you this qualitatively new features. Okay, so let me tell you a bit more specifically the properties of graphene's electrons when they're subjected to this moiré lattice. So roughly speaking, it goes like this. This is the problem that we're faced with. Electrons move in these 2 sheets of graphene, but because they're twisted, they have this periodic kind of structure. The particles sort of see some lattice imposed on them. And the way they see the lattice is the way in which they tunnel between the 2 layers. Okay, they have some amplitude to go from one layer to another, and this tunneling amplitude is sort of modulated by the structure that you can see visually in this. Not very well here, but this is really the size of this new unit cell. And it turns out that there's a special angle that you can associate with the structure. It's an angle it's not some universal number. It has to do with the strength of tunneling between the layers. Okay, so you can come up with a time scale. How long does it take for an electron in one layer to transition to the other layer? And ask how far does the electron in one layer travel in that time? And if there's a commensuration, if there's sort of a resonance for the electron to get to its neighboring unit cell in the same time that it takes to go between the layers. So something like that, if it has some commensuration, something interesting could happen. Yeah, what exactly happens is not clear, but that commensuration occurs at this particular angle around 1 degree once you put in the numbers for graphene. Okay, so people have actually looked at this problem in more detail than what we're saying. They've actually gone and solved for this the problem of electrons moving in these 2 layers, tunneling between them. I won't go into the details, but you can write down an effective Hamiltonian Dirac particles with this tunneling texture, and they've solved for the electronic bands in this setting. There's one small detail I want to mention. When you write down this problem, it looks like there are 2 dimensionless parameters that you'd have to weigh. One of them is the angle, the twisting angle, but there's another one which tells you how much tunneling you get depending on where you are inside this unit cell. Okay, the central point where the lattices are right on top of each other, it's called the AA point. And there's another point called the AB, where one of the lattice sites includes the other one in the other layer, but the others don't. So that's called Bernal stacked graphene. Just take a pair of graphene sheets, don't twist them. They like to form that particular structure. Okay, so in the real system, what happens is that although you overlay it like this, this part of this kind of structure grows. It kind of energetically likes that. So you have to accommodate that in this ratio between these 2 numbers, W0 and W1. Okay, so people have done that, and what they find is that so if you go through the math, allow for these numbers to be slightly different, you end up getting a band structure that looks like this. There's one detail which is called valley. So graphene has these valleys depending on where which Dirac point you're looking at, which of these 2 cones you look at. But if you fix your attention to one valley, previously you had a massless particle, something that had no gap. Now you see that there's some kind of gap has opened up. But right in the center, you have electronic states or electronic band. And as you can see visually, it looks extremely flat. In other words, as I vary the electronic momentum, there is this plane, the kx and ky, the momentum in the plane, the energy barely changes if I'm within this band. Okay, this is what people noticed, Streiser and McDonald and many other people noticed a while back. The thing that's special about this particular angle is that this pancake over here is extremely flat. You move away from that angle, make it larger or a smaller angle, that pancake grows very rapidly and quickly ends up joining the bands above and below. Okay, so you have an opportunity, if you're able to tune this right to that angle, you have an opportunity to have an electronic system with very little dispersion, but you have strong interactions between the electrons and graphene. And we know from past experience, that's a very nice setting to get new physics. Okay, so what this new physics would be, the theorists didn't know, but sounded like a good place to look. So this was out there for a while. People had noticed that the electronic bands become quite flat, but it's really the group of Pablo at MIT working with Jan Kao, who is the graduate student on that project. They really investigated this very carefully, and they produced this phase diagram that was really astonishing when it came out in a few years back. So this needs a little bit of explanation. So what they do is by changing a voltage on this device, they can change the number of electrons that are living inside this very flat band. Okay, and they can go from completely empty to completely full. Those two extremes, nothing very interesting happens. Those correspond to these -4 and +4. Okay, but as you sweep through that band, you're partially filling it, and the band has to do something. Normally, what happens is you just get a metal. Okay, because you have a large kinetic energy, you can roughly forget about the interactions between the electrons. They form a metal because you're within the energy bands. But over here, because of this flatness of the band, very interesting things happen. Okay, and so one of the things that you see there are these integers. So these correspond to filling of this Moire lattice with an integer number of electrons. So you have a pattern. So for example, the integer 1, I've added 1 electron to every one of these lattice sites, or 2 or 3 or 4. And typically when you do that, for example, you add 2 over here, you end up getting an insulating state. Okay, so roughly speaking, that seems reasonable. You have some commensuration. You kind of lock electrons to the lattice sites, you end up getting an insulator. Okay, but at certain other fillings, so the most prominent one is over here, below filling of -2, these domes that you see are really superconducting domes. Okay, and that was a big shock that this system where you try to maximize the effective repulsion turns out to be a superconductor. And the transition temperatures are in the few Kelvin range. So you may scoff at that. We know many elements that have transition temperatures much higher than that. But it's not really a fair comparison to simply look at the transition temperature as an absolute number. We're really talking about a system unlike an element or something at the atomic scale. This is really something where the natural length scale is 50 or 50 times bigger than the atomic scale. It's really related to this very small angle. So 1 degree in radians is 1/50th of a radian. There's a small parameter of 50, 1/50 that's hiding this problem. So a more fair comparison is to multiply energy scales over here by a factor of 50. And then the transition temperatures seem much more robust, kind of approaching what you see in the high TC cuprates. Okay, so that is a more fair comparison. This is a high temperature superconductor if you take it on its own terms. Okay, so the question is, what is happening over here? This is more experimental data kind of plot. When they scan the resistivity as a function of this density, they see these peaks where they see the insulators. But remarkably, at these fillings, the resistivity just drops to 0. That's a superconductor. Okay, so this has been verified now by many groups, by the same group and many samples, and so on and so forth. So really, the task is to understand better these electronic bands and in what is causing this physics. Any questions so far? Maybe I should pause. So what will follow is our attempts at trying to explain this phenomena. So for some people, this may be the best part of the talk may have ended here. Okay, so one of the first things we did was we tried to understand what is different about these bands. Can we relate it to bands that we already knew? For example, in the copper oxides, the other very high temperature superconductor, which was extremely well studied, there's a very good understanding of the bands. You think of electrons sitting on the copper side, they hop around. There's a very good picture of what the bands look like. Are these bands similar to those, or are they very different? Okay, so the general philosophy over here is that it's not just the fact that the bands are flat. That's a statement about the eigenvalues. It's also the eigenvectors, the wave functions that are going to make those bands that are going to be important. And can we characterize them in some way? And of course, the realistic model is very complicated. We took one simplification, which is to switch off this tunneling already reduced on the AA sites. The sites that the graphene lattice does not really like. And then you get a model which is very nice. It has something called chiral symmetry, and you can analyze that more. And one of the questions we were asking is whether this flatness of this band is really an engineering property that somebody found a very clever way to engineer the dispersion to be small, or is there really some science there that really makes it very flat? And you could answer this question if you found a way to make it perfectly flat, no dispersion whatsoever. And if you can do that by just tuning one parameter, it's obviously not engineering. You found some new mechanism to get flat bands. Okay, so we looked at this model, and when we started it, we were just doing it numerically. So of course, all the pictures look much nicer in this model because it has, this sublattice, this chiral symmetry. Everything looks reflection symmetric around zero energy. Yeah, and this is where you start. So I'm starting at for some reason, we parameterize it by this alpha, which is essentially the inverse of the angle. Okay, so when I have very small alpha, it means I have a large angle. At this point, you don't expect much effect of having the two layers. Basically, they're completely mismatched, and the tunneling between them is pretty much irrelevant. This is just the usual Dirac cone that has been folded over many times, and it looks like this. So these are some points in the Brillouin zone. I'm sorry, I'm not labeled it, but this is essentially where the Dirac cones touch each other in the back. Yes, so we're going to look at how this thing evolves as I lower the angle, see how this band structure evolves. Okay, and so you can see as you go down an angle, this central band becomes extremely flat, and that is really that is the magic angle, the 1.05 degrees. And at least in this model, you keep going, you get a lot of dispersion, but then there's a revival. At some even smaller value of the angle, you get a perfectly flat band. Again, at least in this model, it keeps going. You get a whole infinite sequence of these angles where the band is flat. And when we first did this, so this was with a postdoc, Grisha Tanopolsky. So he was doing it in Mathematica, and he said it's really flat. And I asked him, is it completely flat? And he kept pushing Mathematica to its limit, and it did look exactly, perfectly flat. And then we actually found an analytic way to show why this band is exactly flat, at least in this limit.
This angle is the 1.1 degree.
Yeah, that's the 1.1 degree. Yeah. So I used a weird convention where so you see that when this thing gets close to 0.6, 0.59, so use that conversion, you'll get 1 degree. That's the first magic angle. It predicts actually further.
Many magic angles there.
Sorry?
More than one magic angle.
Yes, it predicts other magic angles at lower angles. Now, this is where reality intervenes. If you go to very low angles, there's a lot of reconstruction. So it tries to make it as much like Bernal graphene as possible. So then this model becomes less and less accurate. So around the magic angle, you get it right, even in this limit. So there's not much change of the magic angle between this one and the more realistic models. Okay, so given this, the fact that we have some better understanding of the wave functions, we can now go and add interactions and see what we get here to this model. Yeah.
So since it's related to the tunneling rate, you wanted that angle to be bigger, could you do the tunneling rate?
Yeah. That's a very good suggestion. So one thing people have calculated is that if they were to put pressure, just get these stacks closer to each other, the tunneling rate would increase, and there would be a concomitant increase in the magic angle. And so there's a prediction for how this thing would change with pressure, and that was verified in an experiment. That if they keep the same magic angle and apply pressure, it's kind of like you're not at the magic angle, you don't see much. But then if you realize this and correct it, go to a slightly larger angle, the stuff comes back. I'll show you another very unusual way to increase the magic angle towards the end. But yeah, that has been, that works out nicely. Okay, so now we're going to add interactions, because really what is happening that is new is because of the interactions between the electrons. Okay, so again, I'll have to be a little bit sketchy over here. So let me just tell you the kind of the broad brush the picture of what happens. So we found a way to characterize this band using this kind of model. In fact, not only can you show it's exactly flat, you can find the wave functions of all of the electrons in that band. And one of the things you realize is that this is a band which has this kind of anomalous velocity. If you introduce the anomalous velocity term, it has that anomalous velocity, and it ends up giving you what's called a churn band. So it's very much like a Landau level in the sense that if you were to completely fill it, you get a Hall effect that's quantized, exactly 1. So that is the property of one of these bands. But because of time reversal symmetry, they always come in pairs. Okay, so you can show even at a single value, there's a churn 1 and a churn -1, where the electrons are kind of rotating in the opposite direction. Okay, so that is kind of the basic setup. So you have that at one value, and you have the same story repeating at the opposite value. Okay, so the way in which we think about the insulating states, which appear at these integer fillings, is simply to fill up some fraction of these bands. Okay, and the real question becomes, how do you fill them up? In what sequence do you fill them up to get the best state? And essentially that corresponds to what's called a sigma model. You have to describe these different states in some simplified way. For example, if you pick the state where you fill this band rather than that one, it's like a point on the block sphere where you pick, let's say the south pole versus the north. And you can represent all the other configurations in the space simply by rotating around this block sphere. There's a vector that represents the interacting states. Again, another vector for the other side. So there are a pair of these vectors, n plus and n minus, that can label this manifold of ground states that you get when you have strong interactions that force you to make these choices. And there are some anisotropies. For example, if you fill one of these bands, they have a virtual tunneling process to the other one and back. They like to keep the other one empty. So you end up getting sort of an antiferromagnetic interaction between these vectors. Okay, so to cut the long story short, the way in which you describe these insulating states is in terms of a pair of vectors. You can think of it like that. And these vectors like to be opposite to one another. Okay, you can think of it like an antiferromagnet. There is somehow a pseudo spin that is picked, which is up, another one which is picked to be down. And together they describe the state of the system. Yeah, and so there have been some successes of this kind of picture, which I won't really go into. But there's one very interesting kind of consequence, which is what I'll mainly focus on. What happens when you have an ordered state like this? It's some kind of magnetic state. You can think about it like that. It's the pseudospin is ordered. And this describes the insulating states. And we want to now go away. We want to add electrons and go into the conducting part of the phase diagram, where you actually see the most interesting physics, which is the superconductivity. Okay, and normally in any setting like this, when you're asked to, describe what happens to the electric charge, you have to switch to a different description. Forget about magnetism. Now start talking about what the electrons are doing. Okay, because that is really what is related to the electric charge. Okay, except in this particular instance, where it turns out that a description of the magnetism secretly knows about what the electric charge is doing. Okay, so let me very quickly review this kind of physics, which has to do with Skyrmions. It's sort of well known in the context of this quantum Hall effect. So again, a Landau level that is completely filled, but you're forced to make a choice of spin up versus spin down. That there is something very interesting about topological textures like Skyrmions. So in this setting, the analog of our pseudospin, picking the direction being up or down, corresponds to trying to find a way to describe these the n equal to 1 quantum Hall state. So this is where you have a single Landau level, but you have two spins. It can be either up or down. You're supposed to decide whether it's up or down, a ferromagnetic state. And then you ask, what do I do to add a charge to the system? And the simplest answer to that is that instead of going to the spin up, you have completely filled, let's say, the spin up band. There's an energy gap to go and fill the spin down band, and that's what you pay, and you create a charge. That's normally what happens in a ferromagnet, except over here, it turns out there's a different option, which actually looks very different, which is really this texture of the spins. Okay, you can take the ferromagnet, and instead of keeping them all up, you can make them tip so that they go down in the center, and they have this full texture, which is called a Skyrmion. Okay, and it's known that these Skyrmions, by a simple argument related to quantum Hall physics, you can convince yourself, although that it's a texture of magnetism, they carry electric charge. Okay, so the spin and the magnetism, the magnetism, and the charge properties are all intertwined because they occur inside a Landau level, or equivalently inside something that has this anomalous velocity and the Berry curvature. Okay, so that's a setting where these things are theoretically predicted to occur. In fact, they've been beautifully seen in experiments, maybe actually even here, right? There were NMR experiments by Sean Barrett, where they showed that, if you go and add an electron to this ferromagnet, normal expectation is that you just have one flip spin. But when you actually do the experiment, you add an electron, add one charge, it goes in as a Skyrmion and flips many spins, and you can track the sort of a precipitous drop of the magnetization, whereas this is the more kind of slow drop that you would expect if you had just electrons going in. And more recently, there's been this beautiful visualization of a Skyrmion, charged impurity in graphene. You can go and visualize the Skyrmion there because it's not in spin, it's in pseudospin. And the pseudospin in graphene corresponds to how the charge is distributed in the graphene lattice. And they can go and map out the direction of this the spin vector, the pseudospin vector, and see that single charge impurity ends up, nucleating a Skyrmion around. Okay, so these things are known in the context of quantum Hall effect. What we have over here, at least from our picture, is two copies of this. We have quantum Hall ferromagnet with churn 1 and an opposite churn band because we have time reversal symmetry. And what I'll try to argue is that's a good setting to get superconductivity. Okay, you won't get that in the quantum Hall effect because you're really in a strong magnetic field, but we are managing to get similar kind of physics, but with opposite fields, if you like, because we have time reversal symmetry. Okay, but before I go there, again, maybe there's a very interesting fundamental, very interesting basic point this makes, which is really what is fundamental, right? So normally we like to think about the electron as being fundamental and the ferromagnetism as being a property that arises when you order all the electrons pointing up. Now, actually what you could do is you could insist that actually the ferromagnetism that is fundamental, and the ferromagnetism has a texture, at least in this particular band, that texture carries charge 1. In fact, you can convince yourself it has all the properties of the electron. So you could take this dual point of view that your sigma model is really the fundamental description. It's got this weird excitation, which is charge 1, which is a fermion, and we're going to call that the electron. Okay, so I think it's good to keep in mind that when people talk about fundamental description, that can be a point of view.
I think that was Skyrme's original idea.
Yes, that is Skyrme, yes. Yeah, so that's Tony Skyrme. He wrote this very remarkable paper. I think it was ignored for a long time until Ed Witten wrote a paper explaining how these things fit into sort of modern at that time field theory language, and then it got a lot of attention. So he had a very interesting life. Actually, if you look at his affiliation, he's got that dagger, right? He was at the University of Kuala Lumpur. He kind of moved from his position in the UK and went to Kuala Lumpur for a few years. Also in this paper, actually, I happened to notice, so he has acknowledgement to a very, I guess, a bright vacation student. I think this was like a high school student, probably. And I think there's a typo. I think that's AJ Leggett, Tony Leggett, who's showing some precocious talents.
You could ask Leggett.
Yeah, maybe I should have. Yes, is that how you used to spell a name in the past? Yes. AJ. I mean AJ. Yeah. And I think it's roughly the right time scale. Yeah, so our picture, again, I won't belabor this too much, is that, when you have this insulator, you have these ferromagnet, this opposing ferromagnet, you add electric charge, you decide to dope it. Our picture is that in the simplest version, that charge actually goes in, not as electrons, but as skyrmions. Yeah, and in this setting, the simplest way this charge can go in is one charge to go in as a plus skyrmion in one of these layers, and the other charge to go in as an anti-skyrmion in the opposite layer. Both of them have the same charge because these are opposite charge numbers. And then you can sort of work out what is the binding energy. The two things you need to do to prove superconductivity. First, that there's a binding. And these will naturally have a binding because of this J term that I mentioned, this antiferromagnetic interaction. And the other thing you need to show is that they have an inertia. So if I give you a finite density of them and make them condense, they'll actually form a superfluid that has to do with their effective mass. Here to calculate the superfluid transition temperature of helium-4, you use the effective mass, that's really the inertia. It turns out these objects get an inertia in a very interesting way. It's really an inertia they get because of interactions. Because any one of them is like a particle in a very strong magnetic field. It has a Lorentz force. It sees a Magnus force, but it doesn't move in straight lines. If you bind two of these together, they say opposing fields. And you can do a little calculation to convince yourself that it's really the interaction between them, something like a spring constant, a harmonic spring. You go through the math, and it turns out to be the effective mass of the composite object. It's a little bit like why when you make a smoke ring, or I guess I'm sure most of us don't know how to make a smoke ring, but if you watch one on YouTube, you'll see that the smoke ring is always moving. And it's kind of related to the fact that there is sort of an attraction. These are like vortex anti-vortex pairs. If you take a section, it's a vortex anti-vortex pair. It has some force of attraction, and for that force of attraction to be compensated, it has to keep moving. So there's a relation between the separation between these two, the skyrmion and anti-skyrmion, and their momentum. Okay, so that kind of enters over here, and both of these, it turns out, are set by this effective coupling J. Okay, so if we go and do make an estimate of what is J for the system, it turns out to be a milli-electron volt, about 10 Kelvin. So you'd expect that the transition temperature in this system, very roughly, is some filling, so some number between 0 and 1, which is what fraction of the electrons in the band are filled, times this energy scale of about 10 Kelvin. So it comes out nicely to be about a Kelvin, which is what is seen in the experiment. You can do a more careful calculation, some sort of large N calculation. It's one of the few places I know you can do a large N to calculate the transition temperature. Yeah.
How does this thing overcome the Coulomb repulsion?
Yeah, so the rough picture, so when we do these calculations, we keep the Coulomb repulsion. But roughly speaking, it is that this texture is somewhat big. And that reduces the Coulomb repulsion. And there is sort of an attraction coming from this J. Sort of
the interaction is somehow the exchange interaction, the exchange like prevails over the hard thing.
Yeah, it's something like that. So, there's an analogy to cuprates. The way in which people think of superconductor and cuprates, very bare bones, is that you have electrons sitting on different sublattices, nearest neighbor sublattices, and there is the magnetic exchange J. That's why we call it J over here as well. And that is really what provides the pairing glue. And at least in the cuprates, it seems like there's a lot of controversy about what is the precise mechanism. You go from that to superconductivity, but many things kind of fit, like the rough scale. Cuprates are the largest J of any material. They really are very big because they're right on that. They have all the things going for them. It also gives you D wave very naturally and so on. So this is some analog of that. This is not really on the lattice. It's really the continuum in momentum space in some sense. So it's not a very precise analogy. But somehow this is giving you the pairing glue, while the Coulomb repulsion is kind of lowered by being spread out. Yeah. So we have some numerical calculations which see superconductivity in these setups. Which I won't have time. Actually, you may have heard a talk by Mike Zalatel. So those calculations are getting more and more realistic. At least in principle, what happens exactly in crystal biology graphene is quite complicated. But in principle, you can overcome Coulomb repulsion, get pairing and superconductivity using this kind of mechanism.
Can you control the size of this graphene?
Yeah, so that's related to the anisotropy. So most of our calculations are limit of 0 anisotropy, which is easy to calculate. Then their size is limited by the density. So they kind of go up to the size of the next stuff. Adding anisotropy is hard, especially if you're trying to do large N and things like that. But that's one of the things Zalatel's numerics did. They added anisotropy. They crank up the anisotropy, make it icing-like, then the superconductivity goes away. When it's easy plane-like, it's more likely to be there. Yeah, but that is probably very important. The anisotropy is probably very important. There's no Zeeman field though. It's purely like it's like an n.n kind of anisotropy. Okay, so let me not. This is just to show that within this same calculation, you can get transition temperatures that roughly match. One way to say it is that if this is the sort of the best case scenario, so when you predict for an experiment, it may be an order of magnitude smaller than this. In which case it is slightly, it's off by some factor, which is the usual degradation factor you get from going from theory to an experiment. But there are other compensating things like the dispersion of electrons that we have not added. Okay, so it's it also makes predictions like the transition temperature is linear with doping. It's kind of seen in the experiment. Since TC as a function of doping kind of goes linear, but I wouldn't again put too much weight on this because it's these are not perfectly clean samples, right? So when you think you're doping things in, they may not all be going to the same place. They could be spread out in the sample. Okay, but one thing it did help us with this theory, we don't know if it's right or wrong or it's oversimplified, probably is oversimplified, but it helps you think about new situations where you could get superconductivity. It's way hard to prove a mechanism of superconductivity, but you can try to help it to make predictions. Where else should you look where you have the same ingredients? And hopefully it's better than looking at random. So one thing this theory tells you is you really want to maximize this J. And you can go through some sequence of reasonings and say that the kind of structures you want to look at are ones that have C2 symmetry, rotation symmetry in the plane by 180 degrees. So in terms of the very few structures like that, most of the graphene-based structures, they break that rotation symmetry. For example, people have made bilayers of graphene stacked on other bilayers, those break C2. They're taking graphene structures on something called HBN, which is aligned. They break it as well. So very few structures that actually have that symmetry and have all the other features that we want. Okay, so we actually had earlier we had looked at a certain sequence of structures which preserve such symmetries. Actually, it's due to Islam Khalaf, who was a postdoc in our group at that time. So these are alternating twist structures, multi-layers, not two, but many. So you take one layer of graphene, you twist, stack it on, and take the third and twist it back so that it's aligned with the first layer. And then you can keep going. Okay, so this alternating twist layers turn out to be very easy to analyze because they have only one moiré period. Unlike, for example, you keep turning the layers one after another and generating a screw axis. Okay, those are harder to analyze because they have multiple moiré lattices. So these were very easy to analyze, and Islam was able to do them not just for bilayer, which we already knew, Trilayer, but for any number of layers. And what he found is that the magic angle, this was the first magic angle that we had, it actually appears in the Trilayer as well. Okay, so the Trilayer also has a magic angle, and the band structure, the magic angle again looks very flat, but now you have some additional stuff, which is, it's almost like the third layer got decoupled and it just gave you a dark mode. Okay? But one difference was that the angle has changed. It's actually square root 2 times the original magic angle. So it's at something like 1.59 degrees.
You have 3 layers, you twist one way, the other the opposite way.
Yeah.
The middle one.
Or if you like, the top and the bottom layers are just parallel, and the middle one's twisted. Yeah. And for the 4 layer, you kind of, the second and the fourth are twisted, but they're parallel to each other. So, if you analyze these guys, so then actually the fourth is kind of interesting. You also get a magic angle, but the ratio to the magic angle for 2 layers is this combination, which you may recognize as being golden mean. So somehow that appears, and then it keeps going as you go to more layers. Okay, so, our suggestion to the experimentalists was, why don't you look at these structures? Of course, it looks very hard. You have to do not just 2, but you have to do 3, and there's also an issue about alignment. So it looked a bit dicey, but we anyway made the suggestion. So there's an old kind of, at least in condensed matter, there's this old kind of saying attributed to one Matthias, how to find high temperature superconductors. So he was the real leader before people discovered cuprates and how to find high temperature superconductors. He had a list of rules. High symmetry, cubic is the best. High density is good. Stay away from oxygen. Stay away from magnetism, insulators. So all the numbers 1 to 5, they're all contradicted by the cuprates, right? They're not cubic. They are magnetic. They have oxygen.
Not predicted by cuprates.
Yeah, but 6 was 6 stood the test of time. So we were fighting against 6. Who is going to actually do this? But we found 2 people who had not heard about one Matthias. So these guys attempted this experiment. Philip Kim and Pablo, around the same time they started. We actually talked to multiple people because we thought nobody's going to take us up on this. But turned out this surprisingly works in the sense that they were able to fabricate this 3-layer. They can go to this magic angle, which is square root 2 times what was there previously, and that is the magic angle now. All the phenomena concentrated around there. And they do see superconductivity. In fact, it's a little more robust, it turns out, in this Trilayer as compared to the bilayer. Again, they also had additional degree of freedom. They could tune the electric field, and they could also discover some new things about the superconductivity. You put an in-plane magnetic field, it doesn't couple to anything except the spin. And they were able to show that it's actually spin triplet kind of superconductivity. And so a lot of interesting things came out of this study. People have also now done 4 layers. And again, they went to this golden mean ratio and they see this kind of phenomena. They see superconductivity as well. And 5 layers as well is now being done. So maybe the real surprise for me was the people who did the 5 layers, they tell me it's much easier than doing 2 layers. Somehow, this thing likes to organize in that pattern. Once you get them going, they just lock in. Whereas 2 layers, their yield is like 50%. So anyway, so we don't know exactly what is the mechanism for superconductivity, but I feel this, just like people think about magnetism and cuprates, this J, we think is an important scale, and trying to make that bigger, should somehow feed into the superconductor. Okay, so something I didn't talk about much was a separate thing that occurs in these twisted bilayer graphene samples, the same systems, is that people see the quantum Hall effect. And you heard about Chern number and so on. And in fact, people see the quantum Hall effect called the Chern insulator when they are at a certain one of these integer fillings. And more recently, there has been some signatures of what's called the fractional Chern insulator. So you partially fill some of these bands, put on a weak magnetic field, and you end up seeing the analog of fractional quantum Hall effect. Okay, but unfortunately, I don't have time to talk about this, but just to indicate the richness of this system, not only do you have something that looks like high temperature superconductivity, you also seem to have analogs of the quantum Hall effect and maybe even fractional quantum Hall effect appear. Okay, so let me finish over here. So I give you a story based on Skyrmions. The nice thing about this model is that we derive it from microscopic theory that is inspired by this twisted bilayer graphene, and we go to strong coupling, we can reliably say that this model has superconductivity. It is within the approximations that we looked at. Of course, it leaves out many of the details of the actual system, and that is really something for the future. For example, strain is very important in these systems, and also some of the important dispersion of fermions we've left out, just so that we can keep things soluble. Okay? And both of those things could completely change these conclusions. But at least in terms of predicting new platforms, this is succeeded, and highlighting which directions we should go. Gives you some path that people can explore. Okay, and let me leave you with this picture of my collaborators. Actually, Patrick is here visiting from Harvard, and we had a pedagogical review, which sort of summarizes all of our work. I think I have the citation over here. Actually, now it's on the archive, a pedagogical review of our approach to crystal bilayer. Okay, so let's start again.
Okay, we're open for questions now. Go ahead.
So you mentioned the argument at the beginning that the natural scale, superconducting temperature was somehow related to the moiré length. Can I interpret that to try and understand why, when I start stacking these layers, I get a larger matched angle, which is a smaller length, which is higher temperature? Is that actually?
That's a very good point. In fact,
can you repeat it?
Yeah. So what was noticed is that the magic angle for the multi-layer systems are actually larger than for the bilayer. And can this help us to crank up the energy scales? For example, is this square root of 2 energy scale more than bilayer by previous logic? And is this golden mean times? And actually, that is one of our motivations to think about this multi-layer, also suggested. In reality, something else is there, which is, for example, this Trilayer also has this drag cone. And that gives you a little bit of screening. So it reduces the interaction between electrons slightly because of the presence of additional. It's not a big effect, it's just a drag cone, very small density of states. But it turns out it's enough to negate this increased thing. So we did, actually, Patrick did this calculation, and it turns out you roughly expect the same as bilayer graphene. You go to higher number of layers, you get more and more low energy modes, and that actually tends to overcompensate. So eventually you will end up getting weaker interactions in these multi-layer systems.
I think you have some improvement for trilayer. Trilayer, you definitely get an improvement. But then for 4 layers, so you're at the one velocity, so it's going down, you get more screening. So I think trilayer is probably the best stuff.
Yeah, you get some improvement, but not quite square root 2 kind of.
Not quite square root 2, maybe like 20-30%.
Yeah.
Any other questions?
We have a question from online. Any more insights on angle being golden ratio in 4 layers? Is there a simple formula for any number of layers? Are there any other layers which have a known non-trivial angle like a golden ratio?
Yeah, that's a great question. There is a fairly. Oh, sorry. Yeah. So the question is there some simple formula that gives you all of these ratios of magic angles? And are there other structures? That's what I understood, where you get magic angle-like phenomena. So these angles, actually, in this paper, we have a formula for for any number of layers, and it has some cosines. If you like, you can probably relate it to some. It's really like hopping between these different layers with certain amplitudes that are modified. Yeah, you can find nice analogies why you end up getting these nice numbers. Asymptotically, it asymptotes to square root of 3, so it doesn't keep increasing. But there's a precise formula for that. In terms of other structures, so one very interesting family we've looked at is when you have a stack of chiral layers, like let's say 2 or 3, but they're all banal stacked, like ABC or AB bilayers, and then you twist it and stack it on and put it on top of another chiral stack, so another AB or ABC stack, or even a monolayer. You go to the original magic angle, so this 1.05, you get similar, perfectly flat bands, at least in this ideal limit. But these flat bands can have higher churn number. For example, they can have churn number 2 or 3, and so on. So that's another multi-layer stack that is interesting to explore.
Yes, sir.
The symmetry of the conductor border problem is do we expect any change in the symmetry when you go from this bilayer to the trilayer and so on?
Well, the second part I think is easier to understand, is easier to answer. We don't expect a big difference between bilayer and multi-layers. Some details could change, but if there is a dominant preference for one pairing symmetry, it would kind of go through the entire multi-layer systems. The first one, I think, is really open question. It's not very easy to answer that in a Skyrmion mechanism. It's sort of a strong coupling theory, so maybe it doesn't make a huge difference whether it's S wave or D wave or P wave, because they don't have nodes, at least in the strong coupling picture. It's even experimentally, it's debated what it is. Some people think it has nodes. You look at tunneling spectroscopy, it looks like it has nodes. But then maybe some of you here have talked about how that's a problem for a different kind of set of experiments, the Sandrea tunneling and so on. But yeah, it is a very interesting question. I should say this pairing symmetry can be quite delicate. Although people hold up the example of cuprates, D wave, I think there are other instances, for example, iron pnictides, where you find multiple competing order parameters. And in fact, we think multiple iron pnictides are actually different in the symmetry of the order parameters. So it could be a very delicate balance of things eventually determining the pairing symmetry.
I think we should thank Ashvin for coming and giving us a talk.